All right, so before we get into our actual lab today, we're going to start off with a little demo because we've been spending a lot of time in lecture talking about water and hydrogen bonds. And it's not something that I can actually kind of show you the molecule or show you the bond because it's like a weak attraction. I can't really show you it specifically, but I can show you the effects of the bonds on a big scale. And this is kind of a cool little demo that you can even replicate at home to amaze your family and friends if you want to go that way. So let's see what we've got going on. First of all, I have some wax paper. So what do you know about wax? It's hydrophobic. Remember that word, hydrophobic? What does that mean? Does not like water, right? So let's say that you could see a molecule of wax. What would its characteristics be? What makes it hydrophobic? It does not have any partial charges or even any whole charges. It is completely non-polar. Remember that word, non-polar? Means it has no charges, so it's not going to attract anything. So here we have our wax paper world. And I'm going to introduce you to our little buddy for today. This is going to be Walter, the water droplet. Okay, so here he is. Okay, there is Walter, the water droplet. He's looking pretty cute. So Walter lives in this little wax paper world. And if you look at Walter, he's kind of nice and domey looking. Kind of like a nice round dome. Why is he that shape?
Because the water molecules are holding on to each other.
The water molecules are all attracting each other inside that dome. Now I'm going to zoom in a little bit, and we'll see if we can take Walter for a walk around his wax paper world. This is a toothpick. All right, come on, let's see. Ooh, come on, Walter. Oh, he split. There we go. All right, so look, I can drag him around. Look how cool that is. Woo! Why can I drag him around? What's the property of water that allows the molecules to stick to each other? It's because of hydrogen bonds, and we call it cohesion. Yeah, look how cohesive it is. Woo! He'll stretch. Come on, come on. But one water molecule will tug the ones behind it. You can really go pretty good. All right, so now that this toothpick has got water in the end of it, look, it started off dry. This end is still dry. I'll get a dry one. When I poke him with a dry one, I can drag him. But when I get the one that I used before, it's got water molecules up in the end here, kind of up amongst the wood fibers. When I poke him with this one, look what happens. Isn't that cool? He kind of jumps. He wants to be with his other water molecules, right? The water molecules in Walter are attracted to the water molecules that are up inside the fibers of this toothpick, and he will, there he goes. Kind of cool. So those are hydrogen bonds. You can't see them individually, but working together, you can see their effects. All right, so let's put him up here and introduce you to his best friend. His best friend is Alfred, the alcohol drop. So what's Alfred going to look like compared to Walter? More spread out, right? We think that Alfred might be more like kind of flattened, yeah? So that's because, or why? Why would Alfred look like that? Less hydrogen bonds, right? Alcohol only has a couple hydrogen bonds per molecule. So let's see if Alfred's going to conform to what we expect. Right? 2 drops for Walter, 2 drops for Alfred. They're looking very different. Alfred's definitely, because he is less cohesive. He has less hydrogen bonds happening inside of that drop. So let's see. Do you think we're going to be able to take Alfred for a walk? Probably not. Well, we'll see. Let's get a toothpick. Okay, so I can drag him a little bit, but he's not quite as quite as cohesive as Walter was. He doesn't hang together quite as well because there's only those 2 hydrogen bonds per molecule. The molecules can be separated from each other a little easier than they can in Yeah, with Walter. Okay, so the last of this trio is going to be Olive, the oil. Can you read that? Oil? Olive, the oil droplet. So this is just colored oil, cooking oil. This was water and rubbing alcohol, these two. So let's see what oil looks like. What do you think she's going to look like? What's Olive going to look like?
Thicker in a sense, like, well, I don't want to use the word thicker, but not like alcohol flattened out. I feel like it's going to be more so like
Okay, not quite as flattened as the alcohol, but maybe not quite as domey as the water, somewhere in between, because oil's kind of thick, right? Okay, let's see. Is oil hydrophilic or hydrophobic? Hydrophobic, right? It's non-polar. It should have no hydrogen bonds at all. So you'd think from hydrogen bonding that oil should be the most spread out of all of them, because it should have no cohesion whatsoever. But you're kind of right, because it is looking sort of halfway between the water and the oil. Now, the reason it's looking a little bit domey is not because there's attractions happening. There is 0 attractions in this oil droplet. What is happening is the oil molecules are really big. They're incredibly long, and so they're literally tangled with each other. So the reason the molecules are kind of holding together is not because they have an attraction, it's because they are kind of like a big lump of spaghetti or a big ball of yarn all kind of tangled up together. Where we will see a big difference is trying to take this oil droplet for a walk around the world of wax. Let's see if we can do that. So I can, there's like no, I can't really attract it at all. All I'm doing here is smearing it out. I'm kind of untangling the molecules and stretching them out, but they're not dragging the ones behind them. So I can't really, I can make a nice sun, but I can't drag it around the world as a continuous droplet, because there is no attraction going on inside these, no partial charges or anything inside here. There. All right, so let's move over to another neighborhood here. All right, still wax paper, and see what happens when Walter Part 2 meets Alfred. So let's mix these two together. Do water and alcohol mix?
Oh, yes.
Janaya, why do they mix?
Because they both have hydrogen bonding.
They both have partial charges, they both have hydrogen bonding, so they're going to attract each other, correct? So let's see. I'm going to take Walter over to meet Alfred. It's probably easier. The more you sit, the more it sort of sinks in. There we go. There we go. All right. Now you can actually see the molecules moving. Can you see how they're kind of blah, 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 blah. The water molecules are attracting the alcohol molecules, and it's kind of sucking together, and my blue and yellow liquid is merging together to create a green blob of mixed alcohol and water, because the partial charges on the water molecules are attracting the partial charges on the alcohol molecules. So they're completely mixing together, intermingling with each other. There we go. All right, good. So let's do the same thing with water and oil this time. Go all the way over to the side. What's going to happen with water and oil? They shouldn't mix, right? They should stay separate, because the water would much rather attract to itself than have to be mixed in amongst the non-polar oil molecules. So here we go with some oil. All right, let's see what happens here. So you can see there's a real definite boundary between the water droplet and the oil droplet that you totally didn't have with the alcohol situation, right? And the water molecules are clinging to each other, and they want nothing to do with the oil. They're literally pushing the oil out. They don't want them to get in amongst the water molecules at all. It's a very, very strong boundary. All right, well, let's try one last thing here. Let's try alcohol and oil. Before I do that, I'm going to draw it for you on here what an alcohol molecule looks like, so you don't forget. Alcohol is like this. This is ethanol, or the same alcohol that's in beer and spirits. Okay. Remember our partial charges. So what do we think is going to happen with oil and alcohol? Who's going to take a guess at that one? I'll do it. Maybe where should I do it? Over here. There's the oil. And here's the alcohol. Who wants to guess? A prediction, hypothesis. They won't mix. Let's see. All right. So we can compare. I can zoom in a little bit and bring this over. We can compare how the oil is interacting with the water, or not interacting as the case may be. And we can compare how the oil is interacting with the alcohol. Now, if you look at the difference, the alcohol and the oil definitely, I think you could say, probably has a less hard boundary than you can see between the water and oil. There's a very hard line here. There's no mixing at all between the blue and the yellow. If you look on this one over here, it's a little fuzzy here, and there's a little bit of bleeding of the dark yellow into the light yellow. You guys agree, or am I just making that up? A little bit, kind of, sort of. So if we go back to our alcohol molecule, do you remember how we talked about how we can sort of divide this into two? And the front end of the alcohol molecule has the partial charges. So this is really, really liking water and hating oil. But this end, because it's just carbons and hydrogens, has no partial charges. It does not like water, and it actually would mix quite nicely with oil. So this molecule can't quite make up its mind. Does it want to be with oil? Does it want to be with water? Is it hydrophilic? Is it hydrophobic? And you can sort of see that happening at that boundary between the alcohol and the oil, where it's not a completely cut and dried sharp line like you see with the water molecules on the other example, right? So last but not least, do you think that this alcohol is going to prefer to be with water or with oil? What do you think do you think it's really more hydrophilic, or do you think it's really more hydrophobic? Hydrophilic. People are all around the shop. Let's try. I'm going to put some water on the top edge of this mixture, and we'll see what happens. Is it working? It's kind of sucking the alcohol from the bottom. Can you see this puddle at the bottom should be kind of shrinking away slowly? Kind of hard to see. Let's try a bit more. So the molecules are moving, and the alcohol is being kind of sucked towards the water more than it's wanting to mix with the alcohol, with the oil. And those water droplets are gradually turning green as they suck in the alcohol. Maybe we can see it a little better on this one too. I could put some over here. Ooh, see that droplet? It's moving. It's moving. It's moving. It's got to get there. There it goes. Those are all the molecules being attracted in and rushing in. As the alcohol is getting sucked into the water droplet by those attractions. All right, so last but not least, so that I hope kind of shows that you can see on a large scale the effects of these bonds, even if you can't see the individual bonds themselves. Last but not least, I have a little petri dish here, which is full of just regular water. Just got it out of the tap earlier. Okay. And so because this is water, it's got cohesion going on and then surface tension across the top. Remember we talked about surface tension in the lecture today? And I'm going to sprinkle some black pepper onto the surface of this. And the black pepper are going to behave like little water bugs that we saw in that slide. It's real light, and it can kind of just sit on the surface of the water. It doesn't break through the hydrogen bonding. All right. So if I move this, you can see how the pepper is kind of trapped in the skin of the water. As the water moves, the pepper particles are kind of moving with the skin of the water because they're in amongst that hydrogen bonding, that surface. All right. What I'm going to do next is put a drop of this in there. So this is just regular dish soap. Soap is a really interesting molecule. Soap is actually a hydrogen bond destroyer. So this is a destroyer of the hydrogen bond world. Let's see what happens when I do that. So prepared to be destroyed. Hydrogen bonds. Woo. Okay, you see what happened? So when I put the soap in there, I basically destroyed all that surface tension. I broke all the hydrogen bonds that was causing that surface tension, and the skin of the water kind of shrunk back to the sides. The best thing to think about here is like a balloon. If you imagine the skin of a balloon, right, and then if you write something on it in Sharpie, that's like the Sharpie is like the stuff stuck on the skin, like the pepper was stuck in the skin. And then when you break the skin, when you burst the balloon, the skin of the balloon shrinks back, and all your writing looks all kind of shriveled up and small, right? Like when you do that. That's kind of what happened there. I broke the skin of the water with the soap, and the particles that were trapped in the skin got drug off to the sides as it kind of shrunk away. So the reason why soap works to clean us is its ability to destroy hydrogen bonds. When you put water on your hand, it doesn't want to go on your skin. Your skin is naturally oily for a reason. It's protecting you. It's making you waterproof. And so washing your hands with just water, water is not good at cleaning. Water does not want to get into the nooks and crevices and under your nails and everything on your skin. It wants to stay away from that oil. But if you put soap in with the water, you destroy the hydrogen bonds and you make the water molecules more runny. The water molecules can separate from each other better, and they can get into the under the crevices and under the fingernails and rinse stuff off of your hands. So that's what soap is doing. It's not clean. The soap isn't cleaning you. The soap is making the water molecules more runny so they can clean you. So they're not wanting to stick to themselves. They can separate apart. Hydrogen bond destroyers. Really good. Yes?
So with the thing about water bottles when you're pouring them, if you poured soapy water, would it run?
It should run better, yes, yes. So she was saying, we were talking about when you pour something from a water bottle and it dribbles down the side, or you can see the kind of skin as it kind of teeters over the brink of the bottle. If it was soap in that water, it should run out easier because there should be less hydrogen bonds. Same with when you pour alcohol or liquor. There's less hydrogen bonds, so it'll pour out quicker and smoother and be runnier. All right, it drips more too, so. All right, any other questions? Good questions. All right, you can amaze your third grader at home with food coloring, rubbing alcohol and water. It's all you need.